Hi everyone. We are going to continue our discussion on the k-nearest neighbor. From yesterday's lecture, you may feel k-nearest neighbor is really basic, really easy machine learning algorithm. And I will say you are right on this. But from last lecture, there are quite a couple of things we haven't finished discussing yet. And we are going to start from reviewing the basic idea of k-nearest neighbor, and then we are going to have some discussions. And we want to first focus on the time complexity. We want to answer the question, how fast is the k-nearest neighbor machine learning model? So let's have a quick review on the k-nearest neighbor. The k-nearest neighbor is if we have one item we want to predict, and the easiest way should be we try to find the k-nearest neighbors of the item we want to predict, and then based on the say 5 nearest neighbors, and then those 5 nearest neighbors they are going to do a vote. So if the majority of those neighbors have a certain label, and then I'm going to predict for this item, we are going to try to predict this item should also have this label. So very basic idea of the k-nearest neighbor. And let's just consider a very basic example. So we are going to assume there are m samples for training, n samples for testing, and then there are a total of d features on each of the sample. So, well, we can the number of the features, they can be latitude and longitude, but there can be even more samples. Oh, can you hear the dogs barking over there? I hope you're okay. Okay, so let's see. So we want to know what is the time complexity of the k-nearest neighbor, so for us to predict a total of n samples. Okay, so let me come back here. So I have already said there are n features, there are m training samples, and d features, and n testing samples. Okay, so let's just pick one for example. So if I only have one sample for the testing and I want to make a prediction of that sample, so how can we do that? So we have to find the nearest neighbor, and how do we do that? So that is, even though we only have one item, but we have to find the nearest neighbor from the m training samples. So we have to calculate the distance from this sample okay. We have to calculate the distance from this sample to all the possible samples in the training dataset. Okay, so we have to calculate a total of m distances from the sample we try to predict to all the possible samples in the training dataset. Okay, and how do we do that? Then we have to consider for each of the sample that is actually a vector. So that is a vector of d features in total. So say for the m0, which is the first sample in the training set, it is a vector of d features. And then for the m1, it is the same thing. It is another vector of d features, and and then until the last one, which is m, and it is again a vector of d features. And for this one, for this sample we are trying to predict, it is the same thing. It is a vector of d features. And then also here, d features here, d features here. So if we want to calculate the distance between this sample to this sample, for example, and remember there are a total of d features. To calculate the distance between one sample to another sample, that is OD. Okay, let me come back here. So to calculate the distance between the sample to predict and one sample in the training set, that is a OD. And we have a total of m distances to calculate. That is here. We are going to calculate a total of m distances from each of the training set to the target sample we want to predict. So that will be a distance of a total of m distances. So eventually we are going to have a vector like this. So a distance 0, which is the sample we want to predict, to the m0. And then we have the d1, which is the sample we want to predict, to the m1, and and eventually a dm. So this is all the distances between one sample we want to predict to all the samples in the training data set. And what is the next part? Okay, and the next part we have already come here. So it is OMD to calculate all the distances between one sample to all the training data set. And after that, we want to pick the top K, right? The top K nearest neighbor, which is the lowest K distances. And how do we do that? So we can consider this one. We can consider this vector of distances to be an unsorted list. So how do you find the smallest value from an unsorted list? Well, you can just do a iteration to visit all the items one by one, and then you find the smallest value. And you throw the smallest value away. The next round, you visit all the values again, and then you find the second smallest value. And if you repeat that for a total of k times, and then you will get the lowest k values. So if we want to iterate this thing once, that will be a OM. So we iterate all the items once. However, we want to repeat that for k times, because we want to find the k lowest values. So that will be the OMK. And that is the OMK here. So eventually, we have a OMD to calculate all the distances. And we also have a OMK to pick the lowest k values. And we add them all together, we have the OMD plus OMD plus MK. What is that? That is the time complexity to predict one sample using the k nearest neighbor. And remember, we have a total of n samples. So this means if we want to get all n samples predicted, and then we have to multiply n here. Okay. So this is the time complexity of predicting n samples using a total of m training datasets. Okay. So after here are some more questions. How will a larger training set impact the training time and the testing time of the k nearest neighbor? So there are two questions. How does that impact the training time? And how does that impact the testing time or prediction time? So we can consider first one, the training. So for the k nearest neighbor, in the training part, what do we do? Or do we really do anything? The answer is no. Well, for the training part, actually we just load the data and keep the data, and that's it. So for the k nearest neighbor, for the training part, there's almost no work to be done. Okay, so the answer is, if we have a large training set, well, the cost will be if this training set has already been loaded in a data frame. It is already there. So for the training part, we don't have to do anything. And the next question is, how about the testing part? if we have a big training set, which is the m value is large, how will that impact the testing time? And remember, we just discussed this word. So if the m is a large value, and guess what? The k nearest neighbor will be slower, right? So in the k nearest neighbor, well, if it is not super necessary, you want to stay with a reasonable size of the training set if possible. If you have millions of the records and you want to train machine learning model, you don't really have to use all the samples, especially for the k nearest neighbor, because, well, we are going to calculate a big distance matrix, and this will be super time consuming. And the next part, why do we want to choose a smaller k if we can? So usually we don't want to choose a k value to be 100, for example. If we want to stay with a reasonably small value like 5, 7, we should do that. Why? Again, the answer is here. So this is the prediction time of predicting n samples. And when we have a large k will also make the prediction time or the testing time slower. So that is the analysis part of the k nearest neighbor. Number one, we want to stay with a reasonably small training set if possible. And number two, we want to pick a smaller k if possible. Well, but we have to guarantee that small k doesn't hurt the performance of the k nearest neighbor. So I guess this video is already long enough, and I'm going to pause here, and I will see you later.